All right, here we are. I got to go to lunch here, but I can get this last one done here. And actually, it's not the last one. There's one more, but I'll get it done soon. In any case, this is it for me before I go to lunch this morning. Um, this is double Doppler, but with sound. So it's like you have to use the sound equations technically. And so let's see what happens here. Um, So it's a little bit of a contrived, silly question here. So we have a car blaring a horn. So I have this car that I drew beautifully with this big green siren horn thing that's sending out these waves. And since it's moving, and we have a moving source, these waves, even though they would have 650 hertz, the wavelengths are actually closer to each other. Because remember, when the source is moving with sound waves, it actually changes the wavelengths. And so the wavelengths are actually shorter. And so the stationary observer who's hearing this black, I've marked it in black, sound coming from the moving car is acting as a stationary observer with a moving source. So that's A, just a regular Doppler, plug and chug those equations, very straightforward. So I'm going to call that initial, if nothing was moving frequency, F0. And I'm going to hear the frequency that this person hears to be F1. And then in the car, part B here, in the car, there's somebody that has this special microphone that's pointing and looking at the sound that happens to reflect off of this dude. And that sound is being caught by this car that's moving. Now, the wavelength of the black going this way and the wavelength of the red going this way are the same. I've tried to show that. But now this will cut through those wavelengths quickly, and it'll be like a moving observer, the microphone in the car. So we're going to get F1, which is what this person hears, then the reflected one, and then F2 will be what the microphone in the moving car picks up. So that's pretty cool. So let's do those two problems like in order very carefully, and it's very, very straightforward. So the first half of the problem is the moving car making a noise and a stationary observer. So very straightforward. So let's see what happens. So we have, since we have the moving source, we're using the denominator. Since he's going to hear higher than what we hear, we're going to use a negative. And so we plug in the negative here, speed of sound, the original source, what I called F0, and F1, which is what this person hears, not talking about any reflection or anything, just like a regular Doppler effect, would be about 7,000 hertz. This is unrounded, and then this is rounded. With 2 sig figs, the rounding, I decided to switch it to kilohertz so that I could still have 2 sig figs, have it look nice. Otherwise, it's hard to show 2 sig figs here. In any case, we'll use the unrounded number when we go to do it. So now that reflects, and another stationary observer, like standing here, hearing the reflected, would still hear the 7,000. But this person and this microphone in this racing car coming this way is going to hear a higher pitch, even higher, because this ends up being a moving observer, and you think of this source due to the reflection as having this frequency. So we're going to use this, the answer to the first part, as the given frequency. I mean, I suppose you could make this problem even more contrived, and like this person hears that note and they have perfect pitch, and then they yell out the same note they heard, or something like that. In any case, the red one's the same as the black one coming this way, but the black one is higher than what the speaker would have done if nothing was moving. Okay, so in any case, we're going to use 7,011 in here. So we're going to use 7,011. So F1, the answer to the first part, becomes the frequency here. And now we have a moving observer because it's the microphone in the car that's racing towards the sound coming back to the car that actually has reflected, right? Which is why we have double Doppler for sound. In any case, very straightforward. We're in the top. Since we're moving towards each other, we want this frequency to get even higher. So we're going to use the positive on the top, put a plus 25. and use this 7011 from this answer, becomes the beginning frequency here. And the microphone in the moving car is going to pick up 7,500 hertz, or 7.5 kilohertz is what this red microphone will pick up. And that is double Doppler with sound. It is longer because you got to do the two things, you know, because you actually show the double Doppler in its entirety, because you have the stationary observer who then becomes the emitting source. You have the original source later becoming the observer. When you have double Doppler with sound, you got to be really careful about setting everything up carefully. And that's double Doppler with sound. That's the DDDs for this morning. I'll get another one out to you later today. Thanks a lot, and hope this is going well and you're learning some stuff about waves.